Cool. Hello, everybody. This is Shade and Shape. It's an introduction to Vertex shaders to make computerized art. So just first, an introduction. Who am I? I am Jeff Peck, software engineer. I'm interested in computer graphics. I actually, as I mentioned, I spoke here about fragment shaders last year. Yeah, last year's topic was fragment shaders. Kind of a similar topic, but we'll delve into all that. I work at this place called 10x Genomics. We do, I make software for microscopes that take pictures of DNA and RNA and cells and stuff. And so what are we doing here? Well, hopefully we are getting excited to learn about Vertex shaders. That's so more about what am I doing here. So my goal, what I hope to do, is pique interest that we walk away from here and we have some newfound interest in computer art. We kind of see how easy some of these things are, or maybe we see them as challenging, but either way accessible. Things that aren't like, oh, you need 10 years of experience to do this. Things that you could dive into relatively. But I'm also learning about these topics too. Part of my putting this whole thing together is I'm interested in this, and I wanted to research this a little more and try to make it accessible also for myself. So you'll see in the process of this, kind of at the end, there's a little trial and error that I'm going to talk about. But hopefully we discover this stuff together. So here we go. What is a shader? So it's a computer program. It's a small program that is written in shader language, and it calculates and renders graphics. So it's basically like a big math formula. It's often used for like 3D scenes, like Breath of the Wild down here. But you can also use it for like making art, like that's a fractal. It's called a Mandelbrot set. You can also use it to make very realistic looking images. That's all painted with math by this guy, Nigo Quiles. There's lots of different things. You could make shiny balls and, spheres and things like that. There's all sorts of different types of computational artwork is done inside shaders. Now, the shaders they talk to the GPU, not the CPU. So our computers generally have both. The CPU is for executing single instructions at a time. Sometimes, you can have like 8 or 16 CPUs, but still, it's limited. A GPU is massively parallel, so the idea is you can have lots of these little calculations happen for, say, every pixel on the screen, all in parallel, or roughly in parallel, and that's how GPUs are able to do very fast math and render beautiful things. And we talked about it last year. It almost, in some ways, seems a little bit inefficient because there's a lot of like duplicated work. But in fact, that's how GPUs work. The idea is that everything is doing something, a little bit of some subunit of work together. We can actually leverage the GPU. We can use it with something called WebGL, which is something that's in every web browser. So what is WebGL? It is a little thing. So it's a JavaScript API. Basically, you're writing JavaScript, and you basically, so you're going to provide a list of points. Let's say like vertices, which are attributes. Some custom properties like uniforms. That might be the mouse position or the time, or really any input that just changes. But is kind of like a single number or set of numbers, but nothing huge, like a list of points. And then you're going to write a vertex shader, which we'll get into, a fragment shader. So these things are for calculating the points on the screen and the pixels. And then just a bunch of boilerplate, some common boilerplate. You put it all together, and your web browser does the rest. It's really cool. Then you can literally access and use the GPU. So what is the GPU? Well, so like what is this whole WebGL pipeline? How does it work? So as I said, you kind of start with, you have this list of points or attributes. You might have some other information too, but it's a big, giant list of like all your data, all your vertices really. And then you have some uniforms, which might be, like I said, time or some other variable. All that stuff gets dumped into the GPU memory. The uniforms could get redumped every frame. And then that goes into a vertex shader. So this is the code that converts this list of points into basically another list of points, but everything refers to some coordinate on the screen. Then it gets rasterized. That means all of those points, which might be floating point numbers that just exist in space, they get converted to a single unit, a pixel on the screen. And then each one of those pixels goes into the fragment shader, and that says, what color should this pixel be? That's all it does. For any given pixel, what color should it be? Output a color, and then send that buffer to the screen. And there's all sorts of cool things. This is from Shader Toy. It's just a demo. There's a lot of really cool things that people can make. This is made, by the way, purely with mathematics. There's not. There's textures, but if you look at the code, it's a math formula essentially. Pretty cool. All right. So last year's topic was. It's kind of hard to see, but this was last year's topic, the fragment shader. I wonder if I should turn off these lights. Is that a thing? Should I do that? Yeah. Let's do it. All right, here we go. Nope. Oh, yeah. Okay. Wait. It took a second. Oh, up is off. Got it. Okay, cool. All right. Nice. Oh, it's getting only standing room. Well, there actually are some seats up here. Yeah. Come have a seat. I was just talking about how last year's topic, which you can see right now, was the fragment shader. And what we are going to get into this year is the vertex shader, the whole idea that there's this other thing that is working on the code. So we're going to go straight here. So we're just going to talk about, there's two types of shaders for those just coming in. We're talking about the graphics pipeline. We're talking about how, we have this pipeline. I'm just going to back up like 2 slides so you can see what I'm talking about. This thing. So we have this idea that we are piping a bunch of attributes and properties into a vertex shader, gives us a bunch of points, then that gives us, the fragment shader gives us a bunch of pixels. We're just going to talk about these two things here. So, Arctic and Nicole. All right. So the vertex and fragment shaders, these are written in a language called GLSL, which the L stands for language, just for a second. I think it's a graphics library shading language. Graphics something, shader language. Anyway, the shader language. So it kind of looks like C or C++ a little bit, but it's really simple. There's a lot, it's kind of pared down from a lot of the complexities you find in those languages. So there's like these little programs. They both are responsible for declaring and making use of some runtime properties called uniforms. The vertex shader, this is the first stop of our graphics pipeline. It gets a bunch of inputs, like we said, there's these attributes for a single vertex. So each vertex shader is working on a single vertex. You're going to input thousands of them or hundreds of thousands, but each one works on one thing. And the output is a position in clip space, basically some number between -1 and 1. It might literally just pass the position through. But generally, it's going to do some kind of transformation to make perspective, camera angles. We'll see how all that stuff works pretty soon. And it can access all these attributes you're passing through, and it runs for every vertex, like I said. The fragment shader is the next stop in the pipeline. It gets that position now, but it's on screen space, so it's like a pixel. And its only job is to output a color for that pixel. Your entire fragment shader might just be, for every pixel, the color is red. And that's it. It's just RGBA color space. Cool. One thing, they can pass variables between each other using this varying variable style. It's just worth mentioning. Don't have to get too into that. But and finally, this runs for every pixel or fragment, whereas that runs for every vertex, which might be significantly less than the number of pixels on the screen. Cool. All right, so last year we did talk about, for those of you who were here last year, that's okay, this is not a continuation, but last year we were talking about fragment shaders. So got very into this idea that your vertices might literally just be a rectangle. And inside that rectangle, you're doing all these computations. Now, fragment shaders are really cool because with them, you can do like infinitely complex things. You can compute things like this fractal, which is infinitely complex. This is well, you can make like Menger sponges. A Sierpinski. You guys ever heard of a Sierpinski triangle? It's just the idea. It's a triangle, and as you zoom into the triangle, there's another triangle, and then inside that, there's another more triangles. You know, just infinite triangles forever. So that's what a fragment shader is really good at. Basically, there's some math formula that describes how to draw something, and you just, you know, it's infinite complexity to the level of the pixels that are being rendered. This is also an example. It's not really a Menger sponge, but like some kind of sponge-like thing, 3D objects that have infinite complexity. So there's a lot of really cool stuff you can do that's infinitely complex inside the fragment shader. This year, though, so yeah, just talking about, right, the whole idea, the constraint when we're working in the fragment shader is that everything has to be a mathematical formula. You want to draw a flower, you need, you know, some arctangent function that's going, or a cosine, I forget some mathematical trigonometry function that's going to draw a flower. But in what we're going to focus on today is the Vertex shader. And that is the idea that we're not just constrained to some rectangle and working on, you know, math formulas. We're actually dealing with rigid physical shapes. We unconstrain ourselves from having to only render mathematical models, but now we kind of have this new constraint that we're sort of being boxed in. Kind of like that in the beginning you saw that circle inside a box. It's sort of like a little metaphor in some ways. But anyway, the idea that we're kind of boxing ourselves into something that's more rigid. You know, here's a model that I found on sketchfab.com. And, you know, even though it looks really cool, this dragon, it's, you know, very complex and can animate, but it's still confined to, there's a physical number of polygons, and that's the limit, and there's nothing more after that. Anything beyond that is being shaded, and there's other cool stuff going on, but, you know, now we're working inside limits, and it just kind of changes the way we think about making computerized art. Okay, so we're going to get right into it. We are going to make a triangle. First of all, we're going to be using a library called Regal, R-E-G-L. I think it's pronounced Regal. That's how I pronounce it. And there it is. It's a library. It's a JavaScript library that I talked about. There's a lot of boilerplate. This does all the boilerplate for you. So all you need to do is, you know, is you write you basically write the shaders and very little code just to inject your points and all of that. We'll see how it goes because we're going to make a triangle right now. There it is. So there's our triangle. So just let's see. So this is the code to make the triangle. This is JavaScript. I did say somewhere in the description, you know, this is you don't need programming experience to take part in this. I'm still going to go into this, but if anything's confusing, you feel free to ask questions. So we got our triangle. So there it is, our triangle. It's literally just 3 points. 1, 2, 3. And so we're passing 3 positions in the attributes over there. You can see there are 3 vertices. Count equals 3. Pretty straightforward. And now we get to our shader code. So first there's the Vertex shader. Probably could have done them in opposite order, but fine. The Vertex shader, all it's doing is it takes this attribute position and it outputs the position. It's a 2-dimensional position, so we have to fill in the z, and then the last dimension is always 1 for whatever reason, which I won't go into here. But that's it. So take a position, output the position, but as a 4-dimensional object, taking a 2-dimensional, just, you know, filling in the last 2 dimensions, which don't really apply to a 2-dimensional triangle. cool. And then our vertex shader, our fragment shader, it literally, all it does is it takes this uniform color and it outputs, there's the color. And what's the color? Defined right there. It's red. You see it's RGB alpha. So red, blue, green. So the red channel is 1. The blue and green are both 0. And the alpha channel is 1, meaning it's at full opacity. Which technically would always be the case unless we have other things set up to do transparencies. Okay, cool. So there's our triangle. Any questions before I don't know if I'm speeding through this. We're good so far? Cool. All right. Just talking about the geometries here. We talked about clip space, this whole thing being between -1 and 1 and -1 and 1. So just kind of like, there they are. Cool. Yeah, so I filled that in, kind of made a little grid, and you see there's the 1, 1. That's that position. And all the positions of the triangle are right there. There's a number of vertices. Just, so that's pretty clear. That's all we're doing for our triangle. Now, we're going to take it a little bigger. What if we want to make many triangles, which is generally what we're doing if we're making some kind of shape. So this is an icosphere, which is short for icosahedron sphere or geodesic polyhedron. I had to Wikipedia for that. Basically it's a way of expressing a globe or a sphere. There's other ways to express this. You could imagine globe. Those who work in GIS would know that, or maybe you're familiar with like the UV sphere, more of like a latitude, longitudinal kind of thing. That's not this. This is purely triangles. And I wanted this one specifically because we're talking about triangles, and that's what it all comes down to anyway. So, but you will find usually if you're making like something more globe-like, you would use this other type of object. Anyway, we're just making a simple sphere. And so there is this shape. It's calculated. Again, Wikipedia, it's kind of cool how it's calculated, but it's the nice thing about this, if we want to render this, it seems like, oh, this is going to be very hard, very complex. There is a library in JavaScript called primitive geometry. And again, you don't need to be so familiar with code. Just know we're importing this icosphere from the primitive geometry library, and then we declare it, and that's it. Now we have our sphere. And that's like, this is what I'm going to try to show you guys. Like, this isn't really, just delving into this stuff. You don't need to be a mathematician to know how to calculate this if you want to draw a sphere like this, because there's lots of cool libraries out there, and a lot of this stuff has already been done, and you just, need to know what to look for. Okay, so, but how do we render this icosphere? Well, we remember how to render the triangle. This is, we had our list of positions, 3, and there it is. So what we're going to do here is we'll pass a list of positions and cells. So a little bit different. Obviously, so positions, we just have this list of positions. Cells, instead of passing a count of all the positions, you could imagine, let's say you have this sphere, you have a triangle, and then this line is being reused for this triangle, and then this one's being reused. So there's a lot of reuse. So instead of just passing a list of random triangles that are all connected to each other, we pass this other list of elements. So instead of just having a raw count, we have elements, and what these are just refer to index positions of the positions. So basically, now we have we can reuse points. It's a more efficient way to pass the data, and it works. So so with that, this is what our new code looks like. All we did was add. Let me see. All we did was add a couple lines. So we still have our fragment shader where we just color it red, which was whatever color. And we still have our vertex shader. The only difference is instead of the list of positions and counts, we just have, there's our positions, and there's the elements, and there is our sphere. So what's going on here? Is that it, right? There's our sphere. But is that a sphere? No, it is not a sphere, as it will say right there. We were hopeful that that would be a sphere, but we're still missing something. I mean, it looks round. There's something going on there, but we are still missing some notion of 3D-ness, some kind of 3D shape. So we are passing this list of triangles, so we get this circle. But to render something in 3 dimensions, we need more input, like over here, Johnny 5. I don't know if anyone remembers that, but need more input. So the name for this type of input that we need is called a normal. Let's talk about a normal. So our sphere is composed of a list of faces. Each triangle is like a face. And the face is pointed in some direction. So we need some way to express that. Fortunately, our library, Primitive Geometry, already does provide it. So we get that for free just by using that library. And here's what that looks like. We're literally just adding 2 lines of code. Over there, we're passing in the normals. And then we're going to color the normals. So here we're using that varying. We're going to make the color here and pass it over there from the vertex to the fragment. But also worth noting the normals between -1 and 1. So we just have to make it into something between 0 and 1. We add 1 and divide by 2. So, that way we could say normalize the normal. But so what we get is this now colored circular object. It still doesn't quite look like a sphere, but we're getting somewhere. Just talking about how the normal over there, it's a conveniently a 3-part value between -1 and 1. So all we're doing is assigning a red, blue, green color based on whatever the normal is. It's kind of arbitrary, but it does help delineate things. Now, before we go further, fine. And then we pass the V color, right? Before we go further, I want to just digress onto this sort of side topic here. Did anybody here wonder, why do all the colors appear like a smooth gradient? Aren't we passing a normal for each triangle, each face? Why is it so smooth? Is anyone perplexed or wondering this? I don't know. I wondered this. You understand, because you would think for each triangle there's going to be a single number, this normal, and it's going to look maybe a little more something like this. Because, each thing is like a discrete thing. In fact, though, what happens, we talked about that graphics pipeline, what happens for every pixel value coming off of that vertex shader is it gets interpolated, meaning it gets smoothed out. So you have these very jagged colors, but then just without doing anything, WebGL is going to kind of find the average between everything, so you get these nice smooth colors like we have. Okay, and just talking about that while we're on that topic, the way I was able to even render that is using something called barycentric coordinates. And it's out of scope for this presentation, but there's a lot of cool stuff you can do once you start kind of capturing the edges of the vertices. Again, though, for another topic. Okay, back to our sphere here. So yes, we're rendering these normals, we're coloring based on the value given, but we're still lacking a sense of depth. We don't have any perspective, we don't have any lighting, kind of doesn't look like a real sphere, it just looks like a colored circle in some ways. That's weird how it got all mangled. Maybe the font changed, I'm not really sure why, but that doesn't matter so much, that's the boring stuff anyway. But nonetheless, we need to pass a projection matrix and a view matrix. So this is where we're going to take advantage of the GPU. So you said our computers have GPUs, they're incredibly powerful, and they can do matrix multiplication really, really fast. That's one of the great things about them. So what you can do is all we're going to do is, we're not going to go into how all this works, but you pass something called a projection matrix that will define the camera view. So how are we going to make a projection matrix? We need to study math for 10 years and figure this out. No, there's actually a library called Regal Camera. And all you need to do is import it, initialize your camera. This is just with a nice starting angle, kind of like looking on from the top down, kind of at an angle. And then we update. So for every frame, we take the camera state, and then we render our draw function. And it's like just a few more lines of code, and you can now control it with the mouse, and you can move things around. We need to pass 2 more uniforms to our draw function, and it's going to look like this. Literally, projection, that's a matrix, times view, another matrix, times our position. And that's it. And now, with that, our new position, we will now have perspective. Still not that interesting, right? Because it's a sphere, so it's circular. You don't really have a sense of depth. I added a bunch of other primitives in this. So here's a torus, for example. And there you can kind of see some perspective. Here's a cube, again. And just kind of showing, this is what these things look like without any camera perspective. They're just flat. You can see the normals rendered. But all you do is that multiply by that matrix at that angle, and you get perspective. Our GPUs are basically calculating this stuff 60 times a second or 120 times a second for every pixel on the screen. Or every vertice and then every pixel. So just kind of imagine, it's pretty cool. All right, so now we do have this, but everything's still colored by the normal, by the face. So we can add light. We already added camera, light, camera. So to render light, so we already talked about we were multiplying by the position to get perspective. If we want light, we multiply by anyone, just wild guess, we had positions. The other thing we're using to show the direction something is facing is the normal. That other variable that's in there. So, again, I don't know why the things are a little off, but either way, that's the boring, how that works. Basically, we're taking a dot product now. Now it's not a matrix, it's 2 vectors. And we simply need to add another 2 lines of code. There it is. Take the dot product of the normal and the light direction, which is just literally 3 numbers that say which way is the light pointing. And look at that. Everything is, we have a sense of like a light shining down on these objects now. So we have perspective and lighting. We can see these things rotating. I don't know if I move it around. There it goes to like a completely dark side. Again, this is with really, you saw just a few more lines of code from the very basic thing we started with. And already we're doing some kind of cool, complex, interesting looking stuff. This is the demo I made. I added some controls and stuff, but even that aside, this is all very relatively easy to get into stuff going on. With understanding what it's all about. There's a cylinder. Cool. All right, I'm going to move forward. So now we're going to make some noise with GLSLify. This is just another really cool thing that, we think like what are we going to do with these shapes? They're just kind of boring, primitive shapes. We can, so we're going to use this library called GLSLify, which gives you access to all these pre-made, really interesting, complex, mathematically functions that you can inject right into your GLSL code with, again, 1 or 2 lines added. We are going to use one called noise, GLSL noise, simplex 4D. That's the one. So first we import our library. There it is. We add it. we import it, and this is how we use it. I'm going to go a little bit faster through these because I want to make sure we have time for everything. But ultimately, we are applying this noise function. We import it, and there it is. We multiply we use the position. We pass some modifier, which is one of the uniforms that's coming from outside, but it's just a number. It's like a number between 0 and 1. And then we get our noisy position, and we output that instead of the regular position. And we can get cool stuff, like we can make our shapes kind of dance and wiggle. I also added some other stuff not shown on the other slide to make that kind of shiny effect. Just another GLSL lighting plugin. So, yeah, I think I even toggle the shininess. I don't know if I do, but you can see, you can just make our shapes do interesting, weird things. Cool. All right. So just to summarize up to here, so far we have found that we can use this Regal JavaScript library to render WebGL art in a web browser. Pretty cool. We saw how easy it is to import all the primitives and pass all the vertices to the Vertex shaders. We also found we can apply any perspective just by passing a 4x4 matrix, which we don't have to understand totally how that works, but we know that there's a library that just gives you a camera position, and you can, zoom in and zoom out, and, just now you have a perspective. We can apply lighting just by passing a little vector, which is kind of wild that ultimately, I know there's like more complex lighting models like I showed, but in those later ones, but just that it's literally one little multiplication of the normal times the light direction, or dot product really, and you get this like really cool perspective. And finally, we learned that with GLSLify, there's like just a whole world of these powerful plugins and effects. There's really a lot. I only showed you 2, but there's a lot of stuff out there. Cool. So what's next? So if you look, if you're using Regal, like I showed in these examples, there's a lot of really cool examples they have on their website. Instancing, that means you can have like some object and make 1 million of them, make 1 million dancing toruses, and it reuses a lot of things, a lot of resources, so you can do that. Game of life simulation, kind of like, like cells growing and dying and growing again. Lighting models, like we talked about, line primitives, just kind of 2D line art. You can have audio. Think about, like, you might have seen, like, some demos of, like, something reacting to audio or some kind of input like that. Point clouds. You can imagine, like, 2D games. There's a lot of really cool stuff. So, cloth simulation. These are all demos that exist on Regal's website, and just kind of ideas and things people can have to get started. This is actually one of them. It's literally a body floating in a panoramic view with some reflective properties there. So, just an idea. Cool. But what I wanted to do, just one more thing that I didn't see any demo for on the Regal website. I wanted to, because this whole idea that we're dealing with vertices, we're dealing with very real physical things. So I wanted to try a chair. I wanted to try to render a chair, but like an actual real chair. So why? So it's possible to scan real objects with anyone who has like an iPhone or an Android phone. Most of our modern phones have LiDAR capabilities. You can scan physical objects. And there's a bunch of free apps. It's possible then now you have a list of vertices. So, just pass those in, right? You can take vertices, you can render them in Regal. We can, do this all the same cool stuff. We can make this chair dance, for example. So this is a real chair. There I am sitting in it. Just so you know, this is a real chair. And I downloaded a bunch of apps. I tried one called Scaniverse. That one worked. And it uses the phone's infrared camera, so it makes like a 3D map. You kind of have to sit there and walk around the chair for a few minutes, and then it gets a good image. And then there's also textures stored. I'll show you. This is just what the app produced. This isn't what I did, but this is the 3D scan of the chair that I made sitting in that room. So that's already, I think, like really cool that we can do stuff like that. I wanted to get that, though, into Regal so I can start working with it, do something interesting with it. So just more pictures of the chair, but coming from the scan. Like these aren't photographs. This is like what I scanned. Anyway, so I exported it in this OBG format, which I was hoping would be a nice list of vertices. I used this library called obj file parser. Sounded pretty promising. I didn't worry about the normals. I just wanted the list of vertices. I just want to know if that would work, and here was the result. So, didn't exactly work. So I was very determined. So I wanted to try exporting in another format. This is GLB format, which is actually supposedly more compatible. There's a lot of readers out there that will perfectly handle this GLB format, just free tools out there. But I wanted to get it into Regal specifically. And so I tried this library, Loader's GLTF, which is GLB and GLTF are kind of the same format. One's binary. Anyway, I got a list of positions and elements and should work. Let's see. No, did not work. It was different. There's just, but I kept on having this weird thing where like things were attached. I could not figure out why. So maybe there's something about the formats I'm not understanding. There's lots of tools that can handle these things, but I just wanted to know, like, what can I do? I just wanted to try one more thing. So I used a tool called Blender. It's a free open source tool that lets you edit objects. I was able to read it really nicely, which is awesome. And then I just kind of manually cleared away any vertice that was not part of the chair, just hoping that would work. And then I could just export this clean OBG or GLB, any format really. And no, that didn't work. So at this point, I was updating the slides. I just wrote, this is a learning experience. There's more to learn here, obviously. We're all here to learn things. But so last night at 11:40, I wanted to try one more thing. I just wanted to see if I could get this to work because it's so close. We have a list of vertices. Why can't it just render? So I was like, what if Blender let me export the chair in this STL format, which is a much more. It doesn't even try to do this thing with the cells. It's just a list of triangles. That's it. So, really simple. But it's also a binary format, so I had to figure a whole way to parse the thing I just exported. I found a way that I could basically convert it to JSON and then read the list of vertices. Maybe this would somehow be different. And I got it. Yeah, it works. Yeah, cool. And so what that means is now we can make the chair dance, and that was the whole goal. But really, the idea of taking something physical and just manipulating it, the idea that this is a physical object, now we can apply mathematics to it, and do stuff like that. There's probably other stuff. This was last night at kind of late. All right, so just kind of summing up, we learned about shader language and WebGL and making computer art. Last year we really focused. Well, I focused on the fragment shader and making all sorts of mathematical, computational art. Here we really focused on Vertex shaders and more rigid art, 3D shapes. We learned some basics, just getting started with camera perspectives and lighting, and how to use GLSFI to change things with, basically make a small change that has a very big, profound effect on what we're trying to render. And, of course, there is more to learn. Reflecting on these things. So like the image on the far, my right, your left, is a fractal. That's obviously rendered computationally. The one in the middle is also rendered purely with math. I mean, just sine and cosine functions, to render all the curves and just really some smoothing functions, a lot of linear algebra type of stuff going on there. But it doesn't have to be because it is a very realistic looking object. And then, of course, we have this chair, which literally is a physical object that was rendered, purely from triangles. And, but just kind of reflecting on this idea that, we have like the infinite and then the finite, and we're still applying the same kind of principles. When we have the infinite, we're confining things to pixels, and we have the finite, we're kind of expanding to make it wavy, or apply other math to that. And kind of like this idea we have, you can confine a circle or a sphere, but the kind of like we reflected on last year, sort of like the idea that the whole is in the part, and the part is in the whole, and just nice things to think about. And that is it. Thank you. Cool. Okay. We got questions, comments.
Ooh, questions.
Sure. What's up?
When you're writing the WebGL code, you're writing code snippets within like template strings. What language are you writing there? Is that GLSL?
Yes, that is GLSL inside the template strings.
Cool. My other question is, what's the advantage of using something like WebGL over like 3JS?
I thought about if I used 3JS, a lot of the trying to get the chair would have been a lot easier because there's so many plugins for 3JS that do that. I don't know. I wanted to keep it simple. I've used Regal before, and it's like, I guess 3JS is also. I think 3JS kind of like does a lot of stuff like mysteriously that you don't know, like how did this get here or something. I don't know. I don't have a. Regal.js I have more experience with that.
That's a good reason.
Yeah, I feel like Regal's better for like teaching these kind of things, just seeing what's going on. Maybe.
Does GLSify does it actually change the vertex of the shape, or does it do some kind of like equivalent of a filter on a camera?
Neither. What it really does is it injects a bunch of code. Like if you actually look at like the GLSify. Like the code after you apply that, it's basically just like a lot of functions that.
Is it part of the fragment shader then, or is it still a vertex shader?
I believe in this case, for the noise function, it was in the vertex shader. So it just basically gives you a noise function, and then you can go ahead and use that noise function to multiply by your position. And I was also passing like a value called, I think, time. Or like some modifier, I think, based on the second on the clock, or milliseconds, to kind of seed that noise function. Hey.
Yeah, so I'm just curious. So for the GSL stuff and everything, so for like let's just say for AAA video games and stuff like that, do they use that kind of concept for their sculpting of like the environment, the characters and stuff like that, or is that a whole totally different like language and perspective?
No, it's 100%. It's actually the same. That's what's kind of cool. Like I mean, these games, yeah, the art is way better because they have people sit there and unlike that chair where I'm like, okay, so now, they're sitting there modeling faces and things, but buildings, all sorts of art, but. No, it's the same kind of principles. You have some model, say it's a building, and then you have some fragment shader over it, like to make something look like a rough cement surface that kind of has a reflection because it's wet or something. Yeah. Stuff like that. Actually, I didn't talk about this, but I was thinking about also kind of talking about, there's, in the game Half-Life, there's this awesome, it uses bottles. So like, imagine you have a bottle in the game Half-Life. I've never actually played Half-Life, but I've watched these YouTube videos about it. You pick up a bottle, you see there's liquid in it. So there's like really good simulation of that in the game Half-Life, and the bottle itself is just a very simple, imagine like a primitive shape, but the fragment shader knows all these things about gravity and the last position of it's basically like a fluid simulation or a particle simulation happening in the bottle, and it's really, really cool. If you see some YouTube videos, just Google like Half-Life bottle fluid simulation and you'll see some cool stuff. Cool. Is that it? I think we did it. It's 10:14. We have 45 seconds. Okay, cool. Thank you.